Your tea is getting cold. Right now. As you watch this. And there is nothing you can do about it. Nothing. The universe has decided. It's over for your tea. But before you run to the microwave, stick around, because this daily tragedy is actually the key to understanding the entire cosmos. Subscribe right now so you never miss another deep dive into the weirdest laws of reality, because trust me, you want to be here for what's coming. Okay, but here's the thing, that's not just a minor inconvenience. That's one of the deepest truths in all of physics. The reason your tea cools down is the same reason stars eventually die. It's the same reason you can't build a machine that runs forever. It's the same reason the universe itself has an expiration date. All of that, all of it, comes from one branch of physics called thermodynamics. And once you understand it, you will never look at a cup of tea the same way again. So let's go. First question, what even is heat? Like, actually? Not the vague, hand-wavy heat is energy stuff your 7th grade teacher said before moving on. What is heat physically, in reality? Here's what's actually happening. Everything you have ever touched, your phone, the chair you're sitting on, the air around you, your own body, is made of atoms. And those atoms are never ever sitting still. They are constantly jiggling, vibrating, bouncing off each other like they've had way too much coffee. Wah. And here's the kicker. Temperature is literally just how fast they're jiggling. That's it. Hot coffee has atoms jiggling fast. Cold ice has atoms jiggling slow. Your body is somewhere in the middle, just vibing. So when your hot tea sits in a cold room, the fast jiggling atoms in the tea start bumping into the slower atoms in the air around the mug. And through those collisions, billions of tiny atom handshakes, the tea transfers its jiggling energy to the air. The tea slows down. The air speeds up slightly. The tea gets colder. Done. That's heat transfer. Not magic. Just atoms gossiping with each other. But wait, why does it always go one way? Why does the heat go from the tea to the air and not from the air to the tea? Why doesn't your cold room spontaneously heat up and your tea spontaneously get hotter? That seems like it would be way more convenient. And yet, it never happens. Why? And hold on. We'll get there. Because to answer that, we need the laws. And there are 4 of them. 4 laws of thermodynamics that basically run the entire universe. And we're starting with the weird one, the one they numbered 0. Yes. 0. Not 1. They came up with the Zeroth Law after the first law was already famous and realized, oh no, we forgot something even more fundamental. So instead of renumbering everything, because scientists are stubborn, they just called it the Zeroth Law and moved on. Chaotic behavior, honestly. So what is the Zeroth Law? It says this: if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then A and C are in thermal equilibrium with each other. Thermal equilibrium just means they're the same temperature. They've stopped exchanging heat. Okay, that sounds like math homework. Let me make it real. If your hand feels equally warm touching a wooden table and a metal spoon, then the table and the spoon are the same temperature. That's it. That's the whole law. It just means temperature is a consistent, measurable, transferable thing. It sounds obvious. But without this law, the entire concept of a thermometer literally doesn't work. You can't measure temperature if temperature isn't transitive. The Zeroth Law is why any instrument for measuring anything thermal even makes sense. It's the bedrock under the bedrock. Now, the first law. This one you've probably heard in some form. Energy cannot be created or destroyed. It can only change forms. The total energy of a closed system stays constant. Forever. That's conservation of energy. And it is absolutely ruthless. There are no exceptions. None. 0. Wow. Every joule of energy that's ever existed since the Big Bang is still here, just wearing a different costume. The chemical energy in your food becomes kinetic energy when you walk. That kinetic energy becomes heat when friction slows you down. That heat spreads into the air. The energy didn't disappear. It just changed its outfit. But here's where it gets interesting. The first law says energy is conserved, sure. But it does not say anything about what forms energy can take. It doesn't say anything about which direction things flow. It just says the total amount stays the same. So technically, nothing in the first law prevents your cold tea from spontaneously getting hotter. The math would balance either way. Energy would still be conserved. The first law just doesn't care, which means something else is stopping it. Something deeper is in charge here. And that something has a name. But before we get there, think about this. Every time you've ever eaten food, driven a car, turned on a light, or done literally anything that requires energy, you were working within the limits of the first law. Every engine ever built, every phone ever charged, every star that's ever burned, all playing by this one rule. The universe is a closed system. No energy in, no energy out. Just the same energy, shuffling around forever. Or is it? Okay, so we've got two laws so far. Zero tells us temperature is real and measurable. One tells us energy is conserved always. But neither of them explains the T. Neither of them explains why things go cold instead of hot. Why the universe has a direction. Why time itself feels like it only moves one way. That's the second law. And honestly, N. The second law is the most important law in all of physics. Not because physicists say so. Because the universe runs on it. Here's how it works. And I'm going to use your room as the example, because you already live this. Your room, if you do nothing to it, gets messy. Clothes on the floor. Dishes on the desk. Chaos. And it does this on its own. You don't have to work to make your room messy. It just happens. But making your room clean? That requires effort. Time. Energy. You have to physically go in and put things where they belong. The universe does not help you with this. The universe actively makes it harder. Why? Here's the thing. It's not because the universe is mean. It's because of pure, cold probability. Think about it. How many ways can your clothes be arranged messily? 1,000,000? N? 1,000,000,000? How many ways can they be arranged in the single specific configuration called perfectly clean? Like 1. Maybe 2 if you have a slightly different definition of clean. The point is, there are astronomically more ways for your room to be messy than clean. So, random processes, like you throwing your hoodie somewhere after a long day, almost always land in messy territory. Not because of a rule. Because of math. This is entropy. Entropy is basically the universe's way of counting how many possible arrangements something can be in. High entropy means lots of possible arrangements, disordered, spread out, chaotic. Low entropy means few possible arrangements, ordered, specific, neat. And the second law says entropy in a closed system always increases or stays the same. Never decreases. The universe always moves toward more possible states, not fewer. Your tea cools because there are way more ways for the heat energy to be spread evenly across the room than concentrated in one specific mug. The probability of the heat spontaneously flowing back into the tea is not zero, but it is so astronomically small that it has never happened in the history of the universe and will never happen in any practical sense. You'd have better odds of every air molecule in this room simultaneously jumping to the corner at the same time. Also, technically not impossible. Just really, really not going to happen. And now, here's the moment. Stop for a second. Why? Because this is actually insane. The second law means the entire universe has a direction. Not in space, in time. The reason the past feels different from the future, the reason you remember yesterday but not tomorrow, the reason cause comes before effect, all of that, at the deepest physical level, traces back to entropy. Time moves forward because entropy increases forward. If you watched a video of a shattered mug reassembling itself and jumping back onto a table, you would instantly know the video was playing in reverse. Not because of a rule that says mugs don't unshatter. Because entropy decreasing like that is so improbable it violates everything about the direction reality flows. Entropy is the arrow of time. The universe got that from zero. The Big Bang started in an incredibly low entropy state, everything crammed together, perfectly ordered in its own way. And ever since, entropy has been increasing. The universe has been spreading out, cooling down, smearing energy across more and more possible states. And it will keep doing this. Forever. Until every star burns out, every black hole evaporates, and the universe reaches maximum entropy, a state where everything is the same temperature everywhere. Energy is perfectly spread out, and nothing can ever happen again. No gradients. No flow. No change. That state is called heat death. And it is the ultimate destination of everything that has ever existed. That's where we're going. All of us. The whole universe. Together. Cheerful, right? Okay, so now you understand why perpetual motion machines don't work. You've seen those videos. Some guy in a garage with magnets and a wheel, and the caption, "They don't want you to know about this." And the wheel spins. And spins. And he's like, "See? N. Free energy. Infinite energy. I've defeated physics." Oh. He has not. Here's why. The first law says you can't create energy. You can't get more energy out of a system than you put in. That alone kills most perpetual motion designs. But even if you somehow found a loophole in the first law, which you won't, but hypothetically, the second law kills the rest. Because every time energy transfers or converts, some of it becomes low-quality heat that spreads out into the environment and becomes useless. You can't collect it back without spending more energy than you collected. Every real machine loses energy to heat from friction, from air resistance, from the simple fact that atoms are constantly jiggling and those jiggles go everywhere. The magnets slow down. The wheel stops. The guy in the garage is disappointed. Physics, 1. YouTube inventor, 0. This inefficiency isn't a flaw in engineering. It's not something we can fix with better materials or smarter design. It is the structure of reality. The best engine ever built, perfectly frictionless, perfectly insulated, running in ideal conditions, still can't convert all its heat into useful work. There is always waste. Always. And that was proven in the 1820s by a French engineer named Sadi Carnot, who figured out the theoretical maximum efficiency of any heat engine. It's called the Carnot efficiency, and it depends entirely on the temperature difference between the hot and cold parts of the engine. The bigger the gap, the more efficient you can be, but you will never hit 100%. The second law won't allow it. Entropy will always take its cut. So we've got 3 laws. Zeroth, temperature is real, consistent, measurable. First, energy is conserved, always. Second, entropy always increases. Heat flows from hot to cold, and the universe has a direction. Now there's one more. The third law. And it's short. Almost suspiciously short for something this fundamental. The third law says, as a system approaches absolute zero, the coldest possible temperature, its entropy approaches a minimum. For a perfect crystal, it approaches exactly zero. That's it. But let's unpack it, because absolute zero is genuinely one of the most interesting things in physics. Remember how temperature is just how fast atoms are jiggling? So what happens when you cool something down? The atoms slow down. Cool it more, they slow down more. Keep going. Keep going. Eventually you approach a temperature of 0 Kelvin, which is negative 273.15 degrees Celsius, which is negative 459.67 degrees Fahrenheit. This is absolute zero. And at absolute zero, the jiggling would theoretically stop completely. No motion. No vibration. The atoms just sit there. Maximum order. Minimum entropy. And here's the thing. You can never actually reach it. Never. The third law doesn't just tell you entropy approaches zero at absolute zero. It tells you that getting to absolute zero would require removing every last bit of thermal energy from a system, which would take an infinite number of steps. You can get close. Incredibly, insanely close. Scientists have cooled things down to a fraction of a billionth of a degree above absolute zero. But you cannot reach zero itself. The finish line exists. You just can never cross it. The universe built a wall at the coldest possible temperature and made reaching it physically impossible. That's kind of poetic if you think about it. Now zoom out. 4 laws. And look at what they're really saying together. They're not just a list of physics facts. They're a story. They tell you the universe has a fixed amount of energy. That energy moves around in predictable ways. That it always flows in one direction, toward disorder, toward equilibrium, toward maximum entropy, and that there's a hard floor at the bottom, a minimum possible temperature that can never be reached. Together, these 4 laws describe every heat engine ever built, every living organism that has ever metabolized food, every star that has ever burned, and every cold cup of tea on every kitchen counter in human history. Here's something that breaks a lot of people's brains the first time they hear it. Life, biological life, every organism that has ever existed is a local decrease in entropy. You are a highly ordered structure. You are incredibly low entropy compared to the atoms you're made of floating randomly in space. But you achieve this by massively increasing entropy around you. You eat food, ordered, low entropy molecules, and you convert it into heat, waste, and movement. You exhale carbon dioxide, you radiate body heat, you sweat, you shed dead skin cells. You are constantly dumping entropy into your surroundings so that you can remain locally ordered. You are not violating the second law. You are outsourcing your entropy to the universe. The total entropy still increases. You're just making the universe pay your bill. And every living thing does this. Every cell. Every ecosystem. Even civilization itself is a giant low-entropy structure that survives by burning through the low-entropy state of fossil fuels and sunlight and converting them into high-entropy heat and waste. The second law doesn't hate life. It just means life is never free. Order always has a cost. Someone always pays. So, back to where we started. Your tea. Getting cold. Right now, the atoms in your tea are bouncing against the atoms of the air, trading energy, spreading it out, increasing the entropy of the universe by some tiny, imperceptible amount. In the grand cosmic ledger, your tea cooling down is a universe-scale event. A small, inevitable step in the long march toward heat death. Every cup of cold tea is the universe doing exactly what it's supposed to do. And here's where we leave you. Because there's a question at the edge of all of this that nobody has actually answered. If entropy always increases, if the universe always moves toward disorder, then why did it start so ordered in the first place? Why was the Big Bang a low entropy state? And what set the initial conditions of the universe such that entropy had somewhere to go? Why wasn't everything already at maximum disorder from the very beginning? Some physicists say this is the deepest unsolved problem in all of physics. Not dark matter, not quantum gravity, not the nature of consciousness, but this. Why was the universe born neat? Nobody knows. The laws of thermodynamics tell you exactly where we're going. They say nothing about why we started here. And until someone answers that, the story of heat, entropy, and time remains the most beautiful incomplete sentence in all of science. Your tea is cold now, by the way. If the universe is slowly marching toward absolute disorder, do you think life is just a beautiful cosmic fluke resisting the inevitable, or is entropy itself the very thing driving us to exist? Let me know your thoughts in the comments, and if you haven't already, hit subscribe so you don't miss our next dive into the deep end of reality. Let's see if we can find some order in the chaos.